integration of the parametric form. Now when integrating the Cartesian form, we have everything here in terms of x. So x are limits, y is a function of x, so we're going to have x terms here, then dx. Everything is in terms of x. In the parametric form, everything is in terms of the parameter t in this case. So we have t limits, an example of some parametric equations. X and y are variables, and we have a third variable called t. T is the parameter, hence parametric equations. And you can see from here that dx by dt, if you differentiate this, you get 2t minus 1, you get some t terms to put in here. And y is a function of t, so t to the power 4, for instance, would go in here. So everything is in terms of t. Example 1. So we have two parametric equations, and the area shaded is between x equals 0 and x equals 2. Now we need to know the parameter values for this point and this point on the curve. We know x is 0 here, we know x equals 2 here, but we need to know the value of t here and the value of t at this point. Or parametric integration will all be done in terms of t. So we substitute in x equals 0 here and we solve. We substitute x equals 2 in here and we solve. Okay, so x equals 0 here gives us this equation, and solving gives two values of t. Now only one of these is valid, so if I test both of these values of t for the y coordinate here, so using this equation, so when t equals 0, if I put 0 in here, I've got y is equal to 1 divided by 1, which is 1. That seems like a sensible value. If I put t equals minus 1 into here, the denominator becomes 0. I've got 1 divided by 0, which is undefined. This value here suggests a finite value, not something that's undefined. So t equals 0 is the correct value for the parameter at this point. So we have t is equal to 0 right there. Now for this point, I'm starting off with x is equal to 2. I've substituted that in here. I have this equation. Expand the brackets, take everything to one side. It's quadratic. We solve, we get two values of t. I know the y coordinate here is positive, so what I'm after is the value of t right here. So it's either 1 or it's minus 2. So if I put in 1 in here, I've got 1 divided by 1 plus 1, so 1 divided by 2, that's a half. Y equals a half. That value looks good. If I try minus 2 in here, so then I've got 1 plus minus 2, that gives me a negative value for the y coordinate, which is clearly wrong. So t is equal to 1 at this point. So these will be the limits when we integrate. Okay, we differentiate x with respect to t. So expand the brackets, dx by dt. We need this in our working out. So this is the general form for parametric integration. You need to memorize this. And we have the limits. We have the equation for y is equal to as a function of t that was given. dx by dt we just did. So if we substitute everything in, we have this. And then simplifying, we need to integrate this. And everything is in terms of t. I've done some division of polynomials at this stage. So 2t plus 1 inside the dividend. The divisor is t plus 1. Make sure the terms are in the correct order. Okay, do your division. The quotient goes here, plus the remainder there over the divisor. So this fraction simplifies to this, and we can now integrate. Okay, so integrating, substituting the limits in, and simplifying the final answer. And the method uses this formula. You need to memorize this and remember that everything is in terms of a given parameter. The given parameter could be t, it might be theta, whatever they give you. Example 2, we want to work out the area between x equals 0 and x equals 4. We have some parametric equations. That's the general form that we always start with. So I need some limits in terms of t. At the moment they're in terms of x. So we need to substitute these x values into here and solve. x equals 0, x equals 4, substituting into x equals t cubed, and we've got our two t values here for the parameters. dx by dt, so we need to differentiate 3t squared. So now we substitute everything into here, and we have this. So y was t squared, that's here. dx by dt is 3t squared, that's here. That dt is there. Everything is in terms of t. Simplify, integrate, substitute the limits in, and then our final answer. Example 3, we're given some parametric equations again, and we're looking for the area between t equals 0 and t equals half pi. So we start off with our basic formula for parametric integration. The dx by dt, so if we differentiate sine we get cos, and y is sine t, so we can substitute everything in here and get something all in terms of t, like this. Now there is a double angle here compared to this angle, so if I use the double angle formula for sine, I'll get 2 sine t cos t, so multiplying by that cos t will give me cos squared t, like so. And now there's no standard formula for integrating this, so I'm going to use integration by recognition. So what can I differentiate to get this result? So let's start with cos t cubed. If we differentiate this term, the power comes to the front, reduce this power by 1 here, differentiate what's inside the brackets, differentiating cos will give minus sine there, minus sine, and this looks similar to this. They must be identical, so I need to multiply or divide on both sides by a constant. So if I multiply by minus 1/3 on each side, if I multiply this side by minus 1/3, these cancel. Minus 1/3 times minus 3 will give 1, so this is cancelled. And now I'm still missing a 2 on this side. Now I multiply both sides by 2. So if I differentiate this and get 2 sine t cos squared t, so differentiating in this direction, which is the same as integrating in this direction. So integrating this will give minus 2/3 cos cubed t, like so. Put the limits in and simplify.